So good morning, sorry, good afternoon, everyone, and welcome to this lecture. This is the lecture number 4, and we are hoping to wind up the Biot Savart law in this particular class. In the previous class, we had done some interesting problems of different types of wires and how they were moving and they were going in different planes and here and there. Do you remember these problems? Yes or no? Everyone has understood these problems?
Yes, sir.
Okay. And what we'll do today is quickly move on and see the what magnetic field due to a circular loop on the axis of the loop. Magnetic field on axis of a loop, and we will go through it quickly. We'll not go into the derivation part. We will just see how it looks. We have seen the electric field at the axis of a circular, a ring of charge. This is the magnetic version of the same problem. So what we would have is we would have a circular loop of current, and let me put it here so that I can have. We would have a circular loop of current which is placed centrally here. Current in the loop is I, the radius of the loop is R, and we have a point P on the axis of the loop. What we have to remember is the magnetic field at the point P on the loop, and the magnetic field at point P is given by this revolutionary formula. Magnetic field B is mu naught I by 4 pi. I always keep mu naught by 4 pi. Then this is 2 pi into n into r square. If you don't want to write 2 pi, you can cut this 2 pi and you can just write here as 2 depending on how you want to see it, into x square plus r square raised to the power of 3 by 2. Here you must remember, what is this n? Huh? What is this n? Nagarjun, what is it n? No one knows it. What is this n?
Number of loops.
Number of turns in the loop. If it has one turn, n becomes 1. If there are n turns, it becomes n. This is the magnitude of the magnetic field. What is the direction of magnetic field? And how do you find out the direction of the magnetic field? So to find out the direction of this magnetic field, you can just turn your hands, turn your fingers in the direction of current, and you can see the magnetic field will go in the direction of the thumb. So here the magnetic field direction is in this direction. Do we understand this? It is already shown here by this. Do we understand this? Yes or no?
Yes, sir.
At the center of the loop, my dear friends, at the center O, what is the direction of magnetic field? At the center of the loop also, the direction of magnetic field is like this. If the point P is on the other side of the loop, here, the magnetic field is still on the same side. So remember this. Whether the point P is on right side or left side, the magnetic field is going like this on the axis of the loop. Do we understand this? Or it has gone above our heads saying bye bye?
Understood, sir.
You can do a special case at the center of the loop. At the center of the loop, At the center of the loop, you can just put x as 0 and you will get the formula for magnetic field at the center of the loop. And at the center of the loop, you will get the formula of magnetic field as mu naught Ni by 2R. Yes or no? Huh?
Yes, sir.
Hmm. And you must understand that this is the maximum possible value of magnetic field. Yes or no? This is the maximum possible value of magnetic field that is at the center of the loop. We understand this. So the magnetic field is maximum at the center of the loop. As you go away from the center, the value of magnetic field decreases. We understand this? Yes or no?
Yes, sir.
Then you can remember this small thing, magnetic field at the center divided by magnetic field at any point on the axis where the distance is x. The ratio becomes 1 by x square plus a square into root into 3 by 2. Yes or no? No, yes.
Sir.
Pakka na, sir?
Yes, sir.
Hmm. Hmm. All these are, see, why I'm giving you all these points, so that if you can remember them, there could be a question straight away on this. And if there is a question which is straight away on this, you should be able to recollect it easier. And if you remember it in different forms, it might become easier for you to solve the question. Remember, JEE is a test of your speed, not of your knowledge. So if you can do it faster, you can do it quicker. If x is equal to plus or minus r, where r is the radius, you can see these are the results. At a distance r from the center, it is 2 times root over, I mean, b on the axis is bc divided by 2 times root over. These are different values of r. X is r by 2, r by root 2. These are the, see, why I'm giving you this, because I've seen question based on this. I've seen question based on this. They straight away ask. You just have to put the formula and get the answer. Are you able to understand this? This will also help you in memorizing the formula and getting it inside your heads easily. We understand this. I've also seen questions where they ask you the magnetic field is 1 by 3 times or 1 by 4 times the center of the loop. Then you can use this formula. If b on the axis is b center divided by n, then your x becomes this much. This is nothing, just we have just put the values of different x in the formula, and we have got the answer. Do we understand this? Standard results. I'll give you 2 minutes to note them down. Okay. Then we move ahead, and we also see this small thing. Again, these are all implications of the formula. Magnetic field at a very large or a very small distance, and I've seen a couple of problems in different exam based on this. So if x becomes very large, what we are going to do is put the value of x as very large, and then the binomial expansion and all those things. We can neglect the radius r, and this is the formula that we are going to get. Magnetic field on the axis will be given by this formula, and this is nothing but we have we have neglected r in terms of x. Do we understand this? Neglected r because x is very large. Got this? We got this, bacha? You can
Sir.
simply check all these by putting the value of x as large. You can just neglect x by r and call it as x, and you get your answer. What will be the answer when magnetic field, when the point is very small? You may be tempted to say the answer, sir, it would be same as the magnetic field on the center. It is not. It is this, because then we have to use the binomial expansion. Do we understand this? So remember, the distance is very, very small. The formula takes this shape. The formula takes this shape. If it is very, very small, I'll give you 2 minutes to give me the to note it down. Then we move on and we see the variation of b with x. In one of the sessions, I found a question on this, so I have to do this. There's only once I saw a question on this one, but there has been a question on this one, so we'll have to do this. So we'll do it fast. One question on this I had seen. The bx curve. The bx curve looks like this. You understand the meaning of bx curve? Huh? The variation of magnetic field B with X. At the center, as you can see, what has happened? At the center, as you can see, B is maximum, mu naught, Ni or I by 2R. We understand this, yes or no? Huh? We
Yes,
understand.
sir.
These are 2 points, and again, this has got nothing to do with physics. This has got everything to do with maths. These are known as points of inflection. Have you heard this term, points of inflection? Huh? Points of inflection are the points where the curve changes its shape. Points of inflection. On one point, the curve is having positive slope, and on the other side, the curve is having negative slope. You can understand it in that way. So points of inflection is where the curve changes its slope. The curve changes its shape. These are the points of inflection, and there are 2 points of inflection here. What are the points of inflection here? A dash and A, and the distance between the 2 points from the origin, and that is why we wrote the magnetic field at the point r by 2. It is equal to r. The distance between these 2 points is equal to the radius of the coil where the curve changes its shape. From an increasing curve, it becomes a decreasing curve. Okay, what you have to note down, at this point we have already given the magnetic field, but again you can write the magnetic field in the original form. In the original form, the magnetic field is 4 by 5 root 5 mu naught Ni by r. This is the magnetic field at this point. Both the points, the magnetic field is same, and because of these points of inflection, we have an arrangement which is known as the Helmholtz coil. And I've seen a question based on a Helmholtz coil once in the exam, so I will just go through it quickly. Points of inflection. On one side, you will have a curve whose slope is increasing, and on the other side you will have a curve whose slope is decreasing. So that is the point where inflection occurs. That is all that you need to remember about this point. I've already given you the magnetic field at this point in terms of the magnetic field at the center, r by 2 plus minus r by 2. We have already noted it down. This is the actual result where we have written the magnetic field at the center as mu naught I by 2r. Now this arrangement is used to make for an arrangement which is known as the Helmholtz coil, and this is how a Helmholtz coil look like. Have you noted this down? Huh?
Yes, sir.
Boy, sir? Oi,
Yes,
uncle,
sir.
uncle.
Yes, sir.
Next arrangement is known as the Helmholtz coil. Now this is an Helmholtz coil. You can see same current flowing in the coil, 2 coils in the same direction, not in the opposite direction, in the same direction. Same current flows in the same direction, and the arrangement becomes a Helmholtz coil. And I've seen a question, I think in JEE Advanced I saw it, or JEE Main, I don't remember. But I distinctly remember that saw a question on Helmholtz coil. Same current in the same direction. This arrangement is known as a Helmholtz coil. And remember, the distance between the center is same as the radius of the coils. Here the radius is called as A, so let me call it as A. So what is the Helmholtz coil? It is a setup of, no, I will write it here. It's a setup of, it's a setup of two coils, same radius, same current at a distance which is equal to the radius. This arrangement is known as the Helmholtz coil. Now, why are these coils used? The purpose of having these two coils is to create a uniform magnetic field between the two coils. So this Helmholtz coil will be used to obtain a uniform magnetic field, very short range in between the coils. This is why we use the Helmholtz coil. Do we understand this? Eh?
Yes, sir.
At the
Yes, sir.
midpoint of this coil, and we can easily find both the magnetic fields are going to get added up. Because the magnetic fields have to add it up, therefore the distance has to be same. The radius has to be same. Both the magnetic fields will be added up, and at the midpoint or anywhere in between these coils, we will have the magnetic field which is equal to 2 times of the earlier answer that we have written. The third point you have to remember is current should be in the same direction. If the current is in the opposite direction, the arrangement is not called the Helmholtz coil arrangement. Current should be in the same direction. You can see the current is in the same direction. And the next point that you have to understand is that this Helmholtz coil creates a magnetic field which is uniform between the 2 points. And that is why we use this Helmholtz coil. And this is the resultant magnetic field that you get between O1 and O2. You get an approximately equal, an approximately uniform magnetic field. And this has 3 points of inflection, A dash, A double dash, and A. There are 3 points of inflection. No one is going to ask you the point of inflection. This is just, if they give this arrangement, you should know that diagram looks like this. This is in your code, so they can ask you. I'll give you 2 minutes to note it down. Everyone understands Helmholtz coil? Two coils, same current, same radius, placed at a distance of r from each other. They create a uniform magnetic field. The value is given as this: 8 mu naught I by 5 root 2 5 r. They must carry current in the same direction, and the graph looks like this. I'll give you 2 minutes to note it down. So we move on from this Helmholtz coil to a couple of questions. This is the first question coming on your screens. Ratio of magnetic field at the center of a current carrying coil of radius r to a distance 3r is. I'll give you 2 minutes to give me the answer. So, how do we get the answer for this one, sir? The question is
B center by B axis equal to 1 plus x square by r square whole power 3 by 2.
good. See, if you remember small things, B center upon B axis is equal to 1 plus x square by r square raised to the power of 3 by 2. The value of x is given as 3r. 3r square. R square we can cancel. 3 square is 9. 9 plus 1 is 10. 10 square, 100. 100 cube root, 10 root 10. Sorry, 10 cube is 1000. 1000 root is 10 root 10. So the answer is 10 root 10. Do we understand this? Yes or no?
Yes, sir.
Good. Next one. Do it quickly. Give me the answer quickly so that I can move ahead in life. Next one, this one. A circular current carrying coil has a radius r. The distance from the center of the coil on the axis where the magnetic field is 1 by 8 of its value at the center of the coil is, and I'll give you a minute to do it. So basically, this question require more maths than physics. B center divided by B axis 1 plus x square by r square raised to the power of 3 by 2. B center by B axis. B axis is 1 by 8 times. So B center by B axis become 8. 8 is equal to 1 plus x square by r square raised to the power 3 by 2. So I take 3 by 2 on that side. It becomes 2 by 3. Cube root of 8 is 2. And its square is 4. So 4 will be equal to 1 plus x square by r square. Yes or no? From there, you will get the value of x as r root 3. Everyone understands this? Yes or no?
Sir.
Pakka, sir?
Yes, sir.
Okay, then. That finishes the question on the axis. If you just remember the formula, you can do any question on that circular axis wala loop. Now, before saying final bye-bye to Biot Savart law, we have only seen one way of writing Biot Savart law. That was in the form of current and current carrying element. It can be written in other forms as well, and three forms basically. So now I'm going to show you all those forms together in one table. And this is how that form looks like. This is the normal form of vector law, which we have written, understood, mu naught by 4 pi I dl cross unit vector r by r square or I dl cross r by r cube. It is perpendicular to both dl and r, and the direction is given by the right hand screw rule or whatever. We understand this, yes or no? Huh?
Sir.
Now, instead of current, sometimes you might be given current density, J vector. I've seen a question in JEE Advanced based on this. And that is the reason that I am giving you this formula as well. So, in terms of current density, my dear friends, the formula looks like this. This is just a mathematical interpretation of calculating current and then finding out current density. It is given here, then converting that current density into IDL, So you gets divided by dy, or you multiply it by dy, and that is how the formula looks like in terms of current density, where dv is the small volume of the element. Do we understand this?
Sir.
The third formula is the one where revolutionary things happen. This is a revolutionary formula. This is the formula of magnetic field created by a point charge. Q V cross R by R cube. Q V cross R by R cube. So if I have a point charge plus Q moving with a velocity V, and I have to calculate magnetic field at this point, this would be the radius vector R, and the value of magnetic field will be given by this formula. If you want to write the formula in scalar form, you can write it like this: mu naught by 4 pi. Oops. If you want to write the formula in the scalar form, you can write it like this: mu naught by 4 pi into q v sine theta divided by r square, where what is theta? Theta is the angle between your v vector, velocity vector, and your r vector. This is the scalar formula, so it only gives you the magnitude. It only gives you the magnitude. It only gives you the magnitude. How do I get the direction? To get the direction, what do? I do the cross product of V with R. Do we understand this? So here V is going like this and R is like this. So your magnetic field will be coming towards you. Do we understand this, or this has gone above our head saying bye bye?
That's it, sir.
Bye bye हो गया sir?
That's it, sir.
But remember, this will be the direction of field created by a positive charge. If the charge is negative, you cannot use left hand rule. So how do you find out the magnetic field by a negative charge? You find the field, imagining it to be a positive charge, and then you reverse the direction, you will get the magnetic field due to a negative charge. So magnetic field created by a negative charge, if this was a negative charge, instead of outside, it would have been inside. Do we understand this? Oh, bye bye.
That's it, sir.
Bye bye, sir.
That's it, sir.
Okay, sir. I'll give you 2 minutes to note down these revolutionary formulae. Okay, sir. Then, sir, this question, sir, for you, sir. A proton and an electron. You know the charge of an electron. You can take the charge of an electron as E. An electron and a proton are moving with velocity v. There is a point O, center point. The distance between the two is t. What is the not electric field? What is the magnetic field at point O? And I will give you 2 minutes to give me the answer for this one. Well, you talk about the proton or you talk about the electron, charge of both is same. Electron has a positive charge, uh, proton has a positive charge, and electron has a negative charge. The distance of the point is also same. We just have to see whether the fields are getting added or subtracted. Proton, in which direction it is going to create field? Let me call proton as pink. In which direction is the proton going to create field? V cross B. So the field of proton, the magnetic field of proton will be coming out. Yes or no?
Sir.
What about the field of electron? Is it coming out? Is it going in? Green is the field of electron and it is also coming out. Yes or no?
Sir.
Therefore, both the fields are going to get added up. So your net field will be just 2 multiplied by field created by any charge. What is the field created by any charge? Mu naught by 4 pi charge. Let me take it as E. Velocity is V. Angle between velocity and R vector is 90. So sine 90 divided by distance squared. Distance is d by 2. So it becomes d square by 4. You cut things and you get the value of net magnetic field as 2 mu naught EV by pi r square. That was the answer that we were looking at. Was it such a difficult question? Huh? Was it such a difficult question that you could not do it? Do we understand this? How this is done?
Sir.
What, sir? Understand this, sir, or not, sir? Huh, sir? Arey, we understand it, sir.
Understood, sir. It's d square, sir. In final.
Okay, d square. Shall we move on to the next question?
Sir.
An electron of charge E is moving in a circular orbit. Hydrogen atom, Bohr's orbit, modern physics, structure of atom. With a constant angular velocity omega, what is the magnetic field at the center of the coil? Center of the coil? Center of the circle. What is the magnetic field at the center of the circle? Electron is moving with a constant angular velocity omega. The radius of the circle is r. I'll give you 2 minutes to give me the answer. So how are you going to solve it? There are two different ways in which I can solve this. Method number 1. What is this method
Mu
number?
naught E omega by 2 pi r.
I think it looks. Yes, I think it looks okay. Magnetic field can be given by this formula, mu naught by 4 pi QV sine theta by r square. You can just put this formula, get the answer, and stay happy. B will be equal to mu naught I by 4 pi. The value of charge is E. E. The velocity, if I write the velocity, is omega into r. Omega into r. Theta is the angle between this and this. Velocity and radius vector. Velocity and radius vector. That is 90. Sine 90 is 1. Don't worry about this. Divided by r square. Ding, ding, ding. And we get this answer. It will be mu naught. Why I've written I here? I am probably in some other universe. Mu naught into E into omega by 4 pi r. That is the answer, my dear friends. That is way number 1. Method number 1. Oh, we have to also find the direction. Velocity is like this. Point O is center here. It is coming out. But it is coming out for positive charge. For negative charge, it cannot come out, it has to go the other way, and therefore the magnetic field is going inside. Do we understand this? Yes or no? No or yes?
Yes, sir.
This is method number one, but there is also method number two. How will I find the method number two? In method number two, I will convert this moving charge into current. What is the current created by this moving charge? It is Q divided by the time period T. The charge is E, the time period is 2 pi by omega. So current becomes E omega by 2 pi. E omega by 2 pi. Then I can find magnetic field assuming it to be current. Current I. Current I, center of the coil. What is the magnetic field? It is mu naught I by 2R. I just put the values and I end up with the same answer, mu naught E omega by 4 pi R. Now if the electron is moving like this, then the current is moving like this. So if I take the direction of current, magnetic field is going inside. So I find out from method number one, or I find out from method number two, I will end with the same answer. Do we understand this, or this has gone above our heads? Saying bye bye. Bye bye.
Understood, sir.
Understood, sir.
Anyone got the answer, sir? Understood, sir. So I have to understand that you understand everything, sir. That I understand that you understand everything. Because I am such a good teacher that you understand everything. But are you able to? Did anyone get the answer, sir?
Yes, sir.
Congratulations, sir. I'm very happy, sir, if anyone got the answer. This question may just come in one of your sessions. I don't know which one it is going to come. Okay. Shall we move ahead? Now it's almost the time to say bye-bye to Biot Savart law. But before saying bye-bye, hi. I'll just give you some results that you should remember. You never know what can appear in a JEE paper. You don't need to solve it as such. You just need to remember the results for this one. This is, what should I say? This is infinite sheet, but infinite only in one dimension. In this dimension, oops, it is infinite. Do we understand the meaning of in this dimension it is infinite? So along the y-axis, it is having infinite length, but along the x-axis, it is having width w. It does not have any thickness, so don't worry about the z-axis. Yeah, along y-axis, it is having infinite length, but along x-axis, it is having a finite length, which is given by w. Do we understand this? Huh? Yes or no?
Sir.
Okay. Now, it carries a total current I. Now, this total current is uniformly distributed along the width. So, if you take a small width, delta W or dW or dx, it will have current I by W into dx. Remember, whenever question of current or magnetic field comes, they give you current per unit length. Here, the total current is given. Normally, you might also have current per unit length given. Now, we have a point on the x-axis at a distance a from this sheet of current. The magnetic field due to this sheet of current, you have to break this sheet of current into long parallel wires, infinite parallel wires, find out the current in every wire, and we just need to integrate it. We are not going to get into all those things. We are just going to write the formula. Mu naught I divided by 2 pi W ln natural log of A plus W divided by A. This is how the answer will turn out to be. Sometimes this I by W is given as lambda, current per unit length. Current per unit length. Lambda. If it is given in terms of lambda, then the answer becomes more elegant. It becomes mu naught lambda by 2 pi natural log of A plus W by A. And this is the standard result that you shall never forget, at least not till your exams are over. But I know that if I ask you tomorrow, you will forget it. That's a different issue altogether. My job is to give you all the possible things that can come in a JEE, and that is what I am trying to do. Infinite sheet in one dimension, but finite in the other dimension. Draw the diagram, write the results, and remember it. You have 2 minutes to show your talents. This is the next case, sir. I have drawn the best possible diagram that I could afford. Case number 2, sir. The same sheet, sir. But now the point is here, sir. And I hope you understand the point is perpendicular to this sheet, sir. Do you understand that, sir? Yes, sir, or no, sir?
Sir.
This is the x-axis, sir, and this is the y-axis, sir, and this is the z-axis, sir. This is kept along the z-axis, doing like this. And it carries the current which goes like this. Badang, badang. The current flows like this. The current is I. If I draw a different view of the same, looking from the front like this, it will look like this. It will look like this. This sheet will look like this. I'm just drawing some width of the sheet. Though it does not have any thickness, I'm just drawing it. And it will carry current which is going inside. Do we understand? I've just drawn a different version of the same diagram. So that I can now, this is the point P and this distance is given as R. These, oops. Perpendicular bisector, so these two angles are equal and I call each angle as phi. Each angle is phi. The distance you can see is R. This is the perpendicular bisector. The magnetic field is going inside. Oh, I forgot to. Here, what will be the direction of magnetic field at point A or at point P? What is the direction of magnetic field? I forgot to give that. Yes. What is the direction of magnetic field in this case? Huh? No one knows the direction?
Right, sir.
Inside, sir. Thank you, sir. I thought that I lost it, sir. Inside. Remember it. Direction is important. Here, sir. You understand, sir? This current I is going inside the sheet, sir. Understand, na, sir? Yes, it's going along the minus z axis. You understand this, na? Huh?
Yes, sir. Sir.
Instead of giving the current, I have given you lambda, which is current per unit length. This answer is given in terms of lambda because it is given in terms of lambda. What is the direction of magnetic field at this point? Oh, current is going inside. Now, if you can just apply some common sense, you should be able to tell me the direction. Remember, we have to use the technique of integration again to find out this result. We will take element on this side and element on this side. Something will get cancelled, something will get added up. What is the direction of magnetic field? You can use some common sense and tell me the answer. Yes, current is going inside. Remember, oops. Anyone? Current is going inside. Current is going inside. Doom. Point is on the top. If you turn your hands, it is going like this. That means the magnetic field will go like this. Do we understand what I have written here and drawn here?
Sir.
And write this interesting answer, which does not depend on R. It will create a uniform field here because it is infinite in this dimension. So it creates a uniform field, and the answer, my dear friend, becomes mu naught lambda by pi multiplied by this half angle phi. And that is the answer that you shall never forget. If this question comes, it will be a straightforward question with a straightforward answer that you have to go. You just take this answer and you move ahead in life. Do we understand this, or this has gone above our head saying bye bye? Bye bye, sir. I'm going, sir. Bye bye, sir. Bye bye, sir.
Understood, sir.
Pakka na, sir.
Akka, sir.
Remember the answer, sir. Now there is a different variation of the question, sir, where you have a and I've got this diagram from the book. Have you noted this down, sir? My revolutionary diagram and this ding ding ding.
What is lambda is equal to?
What is lambda equal to? Are they written I by L current per unit length? See, open your eyes. Take a deep breath. Open your eyes and see I by L current per unit length. How much current comes in a unit length in this revolutionary diagram? If this, if this, if this, if this total thing carries current I and the total length is L, I by L is lambda. You understand this?
Sir.
Thank you,
Sir.
sir. Shall we move ahead in life? Life has to move on.
Yes, sir.
This comes the next version of it where it becomes infinite in both dimensions. Infinite in both dimension means it is going in this dimension along x-axis till infinity. It's coming in the x-axis from infinity, and it is also going in the z-axis to infinity. Do we understand this? Infinite in both dimensions. So it is a sheet like this. Infinite, it is kept like this. Infinite in this dimension, infinite in this dimension. We understand this? Previously, it was only infinite in this dimension, and you had found out the field at this point. Mu naught lambda phi by pi. It was finite in this dimension, and you had find out the field here. Now it has become infinite in this dimension as well, and you are supposed to find the field at this point. Do you understand it? So this has gone above and saying bye bye.
Understood, sir.
If I draw my version of the diagram, again I will call this as lambda current per unit length. My version of the diagram would be a pretty simple one. My version of the diagram would be pretty simple one. And I will draw it like this. This is going till infinity. This is going till infinity. Point P is here. In this dimension, it is also going from infinity, and in this dimension, it is also going to infinity. Do we understand this? My version of the diagram? Huh?
Sir.
And it carries current going inside direction. Current per unit length is lambda. At point P, infinite sheet. I will not tell you the answer now. Can you tell me the answer now? What is the answer? First of all, tell me what will be the direction of magnetic field. Current is going in like this. What is the direction of magnetic field? So we don't know the direction. Don't worry. Don't trouble us. Huh? What is the direction? I'm waiting for the direction, my dear friends. Yes? Anyone know the direction or not?
Said, sir.
Same, sir. So much time to take same, sir. Same, sir. B, sir. Same, sir. But one thing you have to tell me also, sir. That is the value of B, sir. What is the value of B, sir? And I wait for your answer patiently. Taking a deep breath. Yes? Yes, sir.
Tata.
Hmm? Are you will you be able to give me the answer or shall I do it?
చెప్తాను మరి.
Yes?
మరి నేను చెప్పాను కదా.
Shall I expect an answer?
Mu naught lambda by pi phi.
Take a deep breath again. What is phi? I have not drawn any phi here. So if you give me the answer in terms of things that are unknown, it is still a question. So you have asked me a question again. So I ask the question back again. What is phi? This sheet has become infinite in this dimension as well. What is the value of phi? What is the value of phi? What is the value of phi? No one knows it. The value of phi is pi by 2. So the answer becomes mu naught lambda by 2. Phi becomes 90. This is the same case of an infinite long wire. The value of theta 1 and theta 2 was pi by 2. Here theta 1 and theta 2 both are phi and phi. Answer is pi by 2. Whatever I do, I am always disappointed. Anyways, I should let go my disappointment and move ahead. Mu naught lambda by 2. This is the magnetic field due to an infinite sheet of current at any point located symmetrically with respect to it. Mu naught lambda by 2 is the answer. Does this mu naught lambda by 2 remind you of something? I know that you can't remember what we had done in the previous class. Now I'm expecting you to remember something we did 15 classes back. That is impossible. Still hoping against hope. Does this mu naught lambda by 2 infinite sheet, does it remind you of something that we might have done in this universe sometimes back? Huh? Something? Something or nothing? Huh? Does it remind you of something? Infinite sheet current, mu naught lambda by 2, something, something, something. It does not remind of us of anything. So I must be in a different dimension when I taught you all that. Yes? Someone was saying anything? Did I hear it correctly or my eardrums were ringing just like that? Eardrums would have been ringing. We had a plate of surface charge density sigma, and we found out the field at this point P. This was the only type of charge distribution that produces uniform field, and the field produced by this charge was sigma by 2 epsilon naught. Now I have the similar thing happening here. Infinite heat, which is infinite in both dimensions. It is infinite in this dimension and it is infinite in this dimension. It carries a charge, no, current per unit length as lambda. At this point P, it creates uniform magnetic field mu naught lambda by 2. This in the denominator, this in the numerator. 2 and 2, they are same. Sigma has been replaced by lambda. Okay, that is just to remind you that we did something known as infinite sheet of charge in a chapter which was known as electrostatics. Sometimes back it was the chapter. I hope when you sleep at night, sometimes you get this deja vu type feeling that okay, we had done that. Okay, we had done that too. For that sake, I'll give you 2 minutes to note it down. Then we have a question, sir. What you see here is 2 infinite sheets of charge. One carrying current in the inward direction, the upper plate, the green plate. Green plate carries current per unit length lambda. In the inward direction, dhar 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 dhar. The other plate carries the same current per unit length, infinite sheet, but in the outward direction. You have 3 revolutionary points. A, in between the 2 sheets. B, up of the top sheet. C, downwards from the lower sheet. You have to find the magnetic field at point A, B, and C. And you have 2 minutes to give me the answer for this one. Let's move ahead and sort it out. This pink one, you must remember that both of these, whether it is the green one or the pink one, both will create the same field, mu naught lambda by 2. This pink one will also create field mu naught lambda by 2. The only thing we have to understand is the direction of field. If they are cancelling each other out, the net field becomes 0. If they are adding each other out, mu naught lambda becomes the answer. Looking at point A, what will be the direction of the pink field? Current is coming out. Point P is here. It will go in this direction. So this field will go in this direction B. Now looking at the lower field, top field, current is going inside. Point is downwards. So if I turn my fingers, it will go in this direction. So both the fields are getting added up. So the magnetic field at point A becomes mu naught into lambda. Do we understand this? Is there anyone on the other side? Do we understand this?
Yes, sir.
Yes, sir.
Looking at point B, due to the lower sheet, current is coming out. Point A, point B is upwards. So still the field goes in this direction. So this field, the pink field goes in this direction. But if you look at the top charge, the field will go in the opposite direction. Both the fields will cancel each other out and the net field would be 0. In the third case, magnetic field due to the first will go here. The magnetic field due to the second one will go here. They will again cancel each out. This is the same of two sheets, two parallel infinite sheets, which we did some time back. One was having plus sigma, the other one was having minus sigma. The field at any inside point was sigma by epsilon naught. At field at any outside point was 0. This is the magnetic variation of the same question. I'll give you 2 minutes to note it down. Let me know once you are done. Then you can note this result number 3rd or 4th or whatever, I have lost count. Now this is not a ring, this is an infinite cylinder. You understand the meaning of infinite cylinder? This cylinder, this is an infinite hollow cylinder and it carries current like this. Current going inside. Do we understand this? Can you imagine this? Infinite hollow cylinder and the current moving like this. If I draw the diagram, the cylinder will look like this. And the current will be moving like this. Do we understand this? What I have drawn is the side view, the view looking from here. Do we understand this?
Sir.
It will look like this, yes or no? It will look
Sir.
like this, yes or no?
Sir.
What will be the magnetic field at the center O if the radius is R? What will be the magnetic field at point O if the radius is R? And the answer would be
0.
0, because everything will cancel out each other, yes or no? This wire will cancel out this wire will cancel out this wire and all those. Do we understand this, yes or no?
Sir.
Pakka sir?
Yes, sir.
Pakka sir?
Yes, sir.
Have you drawn this, everyone? Now I have the same conductor, same cylinder. Now I have the same cylinder. But what I have done is I have cut the total current was I. I have cut a small portion of length dl. I've cut a small portion of length dl. What will be the magnetic field at the center now? If you want, you can take the current per unit length as lambda. You understand the meaning of lambda?
Yes, sir.
Lambda is current per unit length. Now, if I've cut a small segment of length dl from this, so you will have a cut throughout the cylinder. Do you understand what I'm saying here?
Sir.
Do you understand what I'm saying here?
Sir.
What will be the magnetic field at the center? Now you can find out the magnetic field at the center. If the cut was not there, the magnetic field would be how much? Zero, yes or no?
Sir.
So what will be the magnetic field with the cut? Whatever magnetic field is because of the cut, that is the answer. Yes or no?
Yes, sir.
Magnetic field with the cut will be mu naught into lambda into dl. This lambda into dl will give you the length of this will give you the current in this segment. Yes or no?
Yes, sir.
Divided by 2 pi r, because this is an infinite wire whose distance from the point is r. So that would be your answer if there is a cut. Do we understand this?
Yes, sir.
Now instead of this lambda into dl, what they could give you is that they could give you that the total current is I. If the total current is given as I, then you can find out lambda by I by 2 pi r. Do we understand this?
Yes, sir.
Then the answer will become, magnetic field will become mu naught into I into dl divided by 4 pi square r square. Both the answers are same. One answer is written in terms of lambda. The other answer is written in terms of total current I. Do we understand this?
Yes, sir.
Yes or no? Remember
Yes.
this question. This question can appear in your JEE. Main may not be in main, but may be in advance. Note it down fast. I'll give you one more result. Then, sir, this one. This is an infinite half cylinder. So I've cut the upper half completely. Do we understand what I've done? and then this carries current going in the inward direction. Do you understand infinite half cylinder?
Yes, sir.
Let us say that the total current is I. What is the magnetic field at the point O? Just remember the result. And what is the result? The magnetic field is mu naught I by pi square into R. Remember this result. Just remember this result. Okay? Mu naught I by pi square into R. This is a correct result? Yes, correct result. What is the direction of magnetic field if I ask? So again, current is going in this direction. The magnetic field will go like this. All the other components will get cancelled. So just remember this. All the other components. See, this component will cancel out this component. This component will cancel out the vertical component of the other one. So the horizontal components will keep on adding. Do we understand this? This is infinite half cylinder. See, you will not get these questions. I'm just giving you this because if a question comes in JEE Advanced, you can just mark it. This cannot come in JEE Mains. This is just way above the level of JEE Mains. If it comes in JEE Advanced, you can just mark it because you will not have the time to solve it anyways. So even if I tell you how to solve it, you will not be able to do it in the examination hall. Remember the result, mark it, go ahead. Okay. There are two more results that are left. I could not complete them in today's class. Don't worry, I'll give it them in the next class. I'll give them with that formula of Ampere's law. That will come in Ampere's law. Even this will come. This will not come in Ampere's law. That's why I gave you here. The next class, hopefully the last class for magnetic field. The only thing that is left is Ampere's law, and I think we'll be able to complete Ampere's law in the next class. So come in the next class. I think the next class is tomorrow, 1, 2, 3. Be there at 1 so that I can complete your magnetic field by 3. Ampere's law is left. There are some examples that we need to do. There are some results that we need to remember. So be there, and then I'll also take questions from the previous year. So whatever questions have come in this chapter, we will do that probably in tomorrow's class. That's it from my end. Everyone has understood what we have done?
Yes, sir.
Pakka, sir?
Pakka, sir.
Yes, sir.
Keep all these things together. Make them very short so that you can keep them in one page. Whatever results I have given you, I think you can get it in one A4 size sheet. Keep them in front of you. I am sure that one of those questions are going to come in your exam. Okay? These are the tougher ones. Okay, then I'll see you tomorrow. Take care. God bless you all. Bye bye.
Bye, sir.
Bye, sir.
Bye.